So now that we talked about the first law and some thermodynamic processes, let's go ahead and apply it to a couple examples and kind of get a better idea of how all this stuff works. So here we have some sort of ideal gas. So this is 2 moles, so N equals 2 moles worth of monatomic ideal gas. So monatomic just means that it has one particular atom in there. Or at least one species of atom, so there's no mixture of all kinds of different things. And we're going to bring that to state 1, from state 1 to state 2, along a constant pressure. So this is going to be an isobaric process, where in this case we're going to start off at 2 meters cubed worth of volume, expand that to 3 meters cubed worth of volume, and we're going to do that at constant pressure, which has 1 kilopascal worth of pressure. Okay? So from this, what you'll find then is what is the temperature at state 1? What's the temperature at state 2? What is the change in internal energy? And finally, what is the heat which is flowing into the system? Okay. So these are all the quantities that it is that we want to find out. So good. So good. So here we have a PV diagram. As I said before, a PV diagram tells us a lot of information. So it tells us what's the work. Again, that's simply the area under the curve. But it's also going to tell us things about, for example, the temperature. So for example, I would find the temperature at T1 from using the ideal gas law. Right? What we know is that what? The system has to be in thermal equilibrium initially at this particular point. We know the pressure, we know the volume, we know the number of moles, so we can then simply find the temperature. So the temperature from the ideal gas law then is going to be the pressure at 1 times the pressure at, or the volume at 1 divided by the number of moles times then the universal gas constant. So, pulling in our numbers, what we find in this case then is that the initial temperature is 120 Kelvin. Now, to find the temperature at 2, we have 2 ways to do that. So either we can solve exactly the same thing. So we can either say that the temperature at 2 is simply equal to the pressure at 2 times the volume at 2 divided by the number of moles times the universal gas constant, which in this case is fine because we have all these things which are actually given to us. We don't have to rely on something that we actually calculated. Or we can do what we did before, which is simply take the ratio, right? We could also say that the temperature at 2 divided by the temperature at 1 is equal to the pressure at 1 times the volume, pressure at 2 times the volume at 2 divided by the pressure at 1 times the volume at 1. In this case, we know the pressure is constant, so this is simply going to cancel, which means that the ratio of the temperature is just equal to the ratio of the volumes. So in this case, we get the temperature at 2 is equal to temperature at 1 times then the ratio of those particular volumes. Either way, in this case, is absolutely sufficient. Doesn't matter which one that we're actually using, because, again, in the first case, we know everything that's given to us. In the second case, we also know everything that's given to us. Just depends on which one we like better. So in this case, we'll find that this is 180 Kelvin. So good. So the next 2 parts are now we have to what? Calculate. Great. So here we know that what? From the ideal gas law, or not the ideal gas law, sorry, from the first law of thermodynamics, we can determine the change in internal energy. So remember that this is simply equal to the change or the heat plus the work done on the gas. So from here, we can calculate the work done on the gas. That again is just simply going to be the area under the curve from here. But to use this, we would have to then determine exactly what is the heat, right? So we need to know, is heat flowing into the system, is it flowing out of the system, etc. So to do that, we could use the fact that this is what? At constant pressure. So we could, for example, use that this was equal to what? Cp times the number of moles times the change in temperature. But basically to do that, we need to know what Cp is, and to know what Cp is, we need to know what type of gas that this is, but we don't know what it is. We only know that it is what? Monatomic. Mm-hmm. Which turns out that that's actually an easy thing to do. Now, in this case though, let's assume that we don't know what Cp is, so let's ignore that one. What's another way we can do this? Well, another way we can do this is what? we know that here we're not undergoing some sort of particular phase transition, which basically means that what? The change in internal energy then is simply going to be related to the change in temperature, right? Because we know the only thing that's actually changing here is going to be the kinetic energy, which means that here our change in internal energy is simply going to be equal to the change in kinetic energy. But what we also know is what? Because of our kinetic theory, we know that the change in kinetic energy is equal to the change in temperature with some ratio, right? So remember that the kinetic energy was equal to 3/2 m times r times t. Right? Before I wrote that as 3/2 kBt, but in this case we're using it in the number of moles, which means in this case our change in kinetic energy is simply equal to 3/2 times n times r times the change in temperature. So in this case, we can find our change in internal energy is actually equal to 3/2 times n times r times the change in temperature. It turns out that this thing and this thing are actually the same, because it turns out for monatomic gas, Cp is actually equal to 3/2. But if I didn't know that, I could just use this expression. It'd be exactly the same. If I was dealing with a different type of gas, then that number would actually change, and so would this number here. So if I was dealing with a polyatomic gas or a diatomic gas, that number is actually going to be different, but let's not worry too much about that. So good. So basically plugging my numbers here, what I find is this works out to be 1500 joules. So this is my change in internal energy. Good. Now from here, we can now use the first law to then determine exactly what is the heat flow into the system. So again, let's assume that we don't know what this is. So in this case, what we can say then is that what? So this is going to be equal to, so Q then is going to be equal to the change in internal energy minus the work done then on the gas, which is going to be the same thing then as what? The change in internal energy plus the pressure times the change in volume. Plug this in. What I get in this case then is that this works out to be about 2,500 joules. So let's do another example. Next one is going to deal with an adiabatic process, so we can kind of get used to what that thing is actually saying. So let's look at an adiabatic process. This time. So this says that we have a volume of an ideal gas is adiabatically reduced from the initial volume, let's call that V1, equal to 200 liters, to the final volume, let's call that V2, which is equal to 74.3 liters. The initial pressure and temperature are, so we also know that the initial pressure is equal to 1 atmosphere, and the initial temperature is equal to 300 Kelvin. And the final pressure, so P2, we know then is equal to 4 atmospheres. So the first thing I want to know is part A, is our gas monatomic, diatomic, or polyatomic? That's going to relate to those different CP values that I kind of mentioned. And then for B, we want to know what is the final temperature. So what is T2 equal to? And then finally, for part C, we want to know how many moles of gas are there. Okay. So good. So first off, how do I know if this thing is monatomic, diatomic, or polyatomic? Well, that's all going to depend on that factor of gamma. So before what we wrote was that what? We had to have the pressure times the volume raised to the gamma was equal to some sort of constant. Right? So in this case, we can use this to then determine exactly what is this value of gamma. Once we know that value of gamma, we're simply going to again look in the textbook, find there's a table which basically says that for monatomic, gamma has to be this, diatomic gamma has to be this, and then for polyatomic, gamma has to be this, we're going to match whatever the gamma value is that we get and then determine what type of system that it is. So, good. So what do we know? So here we know what? We know the initial and the final volumes. We know the initial and the final pressures. So what that means is, since this thing has to be constant, what this means then is that the initial pressure times the initial volume raised to the gamma must then be equal to the final pressure times the final volume raised to the gamma. So, since we know all these quantities, we can then now isolate what gamma actually is. So to do that, let's go ahead and take a ratio. So I'm going to divide both ways. So I'm going to write this then as, let me bring the p to this side. So I'm going to have P2 divided by P1 then is equal to what? V1 divided by V2, all raised to the gamma, right? Good. So now, what I want is that gamma. So to bring that gamma down, we're going to simply take a natural log. Right? We wrote this in the last video, but remember that natural log of some quantity A raised to the alpha is the same thing as alpha times the natural log of A. So this is the property of natural logs. So in this case, if I take a natural log of both sides, this is going to be the same thing then as gamma times the natural log of the ratio of the volumes must then be equal to the natural log of then the ratio of the pressures. Right? So good. From here, this simply says then that's what? Gamma then is going to be equal to the natural log of the pressures divided by the natural log of the volumes. Right? So basically, if I do that, this then tells me that gamma then is going to be equal to 7/5. And when I look up in that chart, what I find in this case then is a gamma of 7/5 corresponds to a diatomic molecule. So this thing is diatomic molecule. Great. Good. So now, we want to know what is the temperature at that point. Well, again, as we talked about when it came to adiabatic systems, what has to be true is, for part B, that the temperature times the volume raised to the gamma minus 1 must also be equal to a constant. So in this case, since I know the initial temperature and I know the initial volume, and I know the final volume but I don't know the initial temperature, then I can find the final temperature by simply saying that what? The initial temperature times the initial volume raised to the gamma minus 1 must then be equal to the final temperature times the final volume raised to the gamma minus 1, which means then that the final temperature is equal to the initial temperature times then the ratio of the initial volume to the final volume raised to the gamma minus 1. We now know what gamma is. Again, from part A, gamma is simply equal to 7/5. So I can use that and plug that in. So in this case, what I find is this works out to be 455.8 Kelvin. Great. So part C, we now want to know what is the number of moles. Well, find the number of moles. This is an ideal gas. Whether it's monatomic, diatomic, polyatomic, it's still ideal. Which means then, this thing has to also satisfy the ideal gas law at any point. So it doesn't matter what that point is, it just has to satisfy that ideal gas law. So, here, since we already know everything at the initial point, let's use that and then determine the number of moles. So using the ideal gas law, I have to have the pressure 1 times the volume of 1 must be equal to n times r times the temperature of 1. Which means that the number of moles is going to be the pressure at 1 times the volume at 1 divided by r times the temperature at 1. Like our numbers, I find this turns out to be 8.1 moles. So these are some kind of examples. We'll do some more examples later, especially in the group assignments that I just posted. Those have a lot which deal with those different types of thermodynamic processes. We'll talk about those. Kind of how to do those when we all meet on Zoom. But yeah, so otherwise, the next section we're going to talk about then are, so far we've talked about heat flowing from one system to another system, but now we need to talk about how that actually happens. So we're going to talk about mechanisms of how heat is going to transfer from one system to another system. So what are avenues that this is going to allow, or avenues that allow for heat to flow? And so we'll do that in the next portion.